On April 8, 2026, the Denver Board of Water Commissioners approved Stage 1 drought restrictions for the first time in years. Customers are required to cut their water use by 20%. Parks and public green spaces must reduce irrigation by 20%. The reason is visible in one number. The snowpack in Denver Water's Colorado River Basin collection area peaked on March 18, 2026 at 58% of normal, the second earliest peak date on record, and then it fell off a cliff. By May 18th, the snowpack was at 0% of normal, the lowest ever recorded for that date. Not near the bottom. The bottom. The 2025 to 2026 winter was Colorado's warmest on record by a large margin, with record-breaking heat events in March that eliminated snowpack weeks earlier than any previous year. Denver Water serves about 1.4 million people across the Denver metropolitan area, one of the fastest-growing major cities in the United States. Almost all of that water starts as snow in the Rocky Mountains. This year, there was not much of it. And what fell melted faster than any year on record, running off before the reservoir system could capture it. I'm Benjamin, and this is Watts Around the World. To understand what the snowpack collapse means for Denver, you have to understand how the city's water system actually works. Denver Water captures water from two systems, the South Platte River Basin to the south and the Colorado River Basin to the northwest. The water that falls as snow in those mountain watersheds stays frozen through winter, then melts gradually through spring and early summer, flowing into streams and rivers that feed into Denver Water's reservoirs. Those reservoirs, Dillon, Gross, Williams Fork, Cheeseman, and others, store that runoff and release it throughout the year to meet demand. The mountain snowpack is not just precipitation. It is a giant natural reservoir, storing water in frozen form from October through April, releasing it slowly when the city needs it most. Climate change is attacking this system in two ways simultaneously. First, temperatures are rising. Colorado has warmed by approximately 3 degrees Fahrenheit since the 1890s, with 9 of the 11 warmest years on record occurring since 2012. Warmer temperatures mean more precipitation falls as rain rather than snow, which runs off immediately rather than being stored until spring. They also mean that what snow does fall melts earlier and faster. The Colorado State University Climate Center described the 2025 to 2026 season's warmth as unlike anything previously observed. Second, and more insidiously, the timing of the snowmelt is shifting. Even in years with adequate snowfall, the melt is arriving earlier in the calendar year, producing high early season flows that the reservoir system cannot fully capture and leaving lower flows in late summer when demand peaks. The hydrograph is flattening and shifting left. Water that used to arrive in May and June is arriving in March and April. Infrastructure built to capture April through July, runoff is being outpaced by a changing climate that moves water through the system faster than it was designed to handle. Denver Water has been managing this pressure for years. The Gross Reservoir Expansion Project near Boulder, one of the most controversial water infrastructure decisions in Colorado in decades, was specifically designed to add 77,000 acre-feet of additional storage to make the system more resilient to exactly the kind of year 2026 has turned out to be. It is a multi-hundred-million-dollar investment in catching and holding more of the water that does come down from the mountains before it flows past the city and is gone. But there is a different kind of loss happening simultaneously, one that has nothing to do with storage capacity and everything to do with what happens after water is captured. Colorado loses water to evaporation on a massive scale, and most of that water is leaving through surfaces that could be covered. Colorado has been in a near-constant state of drought since the early 2000s, and the trend is accelerating. Colorado has approximately 17,000 miles of mainline irrigation canals, running primarily through lower elevations and the eastern plains. These canals carry water from mountain snowmelt to farms, cities, and industries across the Front Range and beyond. They are the arteries of a water system that sustains Colorado's agriculture and its cities. And they are open to the sky. In Colorado's dry, hot, windy summer conditions, open water surfaces lose water to evaporation at a significant rate. According to a state feasibility study published in early 2025 by the Colorado Water Conservation Board, Colorado's irrigation canals lose approximately 90,000 acre-feet of water per year to evaporation. Solar panels installed over those canals could cut those losses by up to 22,500 acre-feet per year, even if panels were only installed over a portion of the network. That number sits inside a much larger one. Colorado has 1,900 reservoirs identified as suitable for floating solar installations. The total annual evaporation from those reservoirs is slightly more than 600,000 acre-feet. To put that in context, Colorado's cities and towns use approximately 380,000 acre-feet of water per year in total. The water evaporating from Colorado's reservoirs annually is greater than the water consumed by every city and town in the state combined. If every suitable reservoir deployed floating solar panels, the feasibility study estimated that evaporation losses could be reduced by up to 407,000 acre-feet per year. That is more water than Colorado's cities and towns use in a year, recovered from surfaces that are already built, already holding water, and currently doing nothing to protect the water they contain from the sun. The county with the greatest evaporative losses from reservoir sites is Weld County, followed by Larimer, Crowley, and Park counties. These are not remote, inaccessible locations. They are the agricultural heartland of the Front Range, connected to road networks, electrical infrastructure, and the communities that depend on the water stored in those reservoirs. If stories like this are what you follow, please subscribe. Watts Around the World puts out a new video every week. Colorado's feasibility study was not produced in isolation. It was produced in the context of a national policy shift that has been building since 2022. The Inflation Reduction Act included $25 million specifically directed to the Bureau of Reclamation to design, study, and implement solar panels over federally managed water conveyance facilities. The Gila River Indian community in Arizona completed the first solar canal project in the Western Hemisphere in October 2024, demonstrating a 40 to 65% evaporation reduction on the covered section of the Casa Blanca Canal. California's Project Nexus on the Turlock Irrigation District Canals went fully operational in 2025. Both projects fed data into the national conversation about where solar canals work best and what they cost to build. Colorado's feasibility study was the state's formal response to that national momentum, translating global experience into specific projections for Colorado's own canal and reservoir network. Denver Water sits at the center of that conversation. Dillon Reservoir, the largest body of water in Colorado's mountain region and one of Denver Water's primary storage facilities, sits at over 9,000 feet elevation in Summit County. It is surrounded by Rocky Mountain terrain and fed by the Blue River and its tributaries. It loses water to evaporation throughout the summer months. The feasibility study identifies reservoirs like Dillon as part of Colorado's floating solar opportunity. Though the high-altitude environment introduces specific engineering considerations, including snow loading on panels in winter, wind exposure from mountain weather systems, and the longer construction season limitations that come with Colorado mountain locations. The Stage 1 drought restrictions that Denver Water imposed in April 2026 require a 20% reduction in water use across the system. They were accompanied by drought pricing, a tiered rate structure that charges higher prices for higher use, designed to send a financial signal about the scarcity value of water during drought periods. Denver Water's board made that decision in direct response to the worst snowpack on record and reservoir storage levels, tracking well below average through the spring. The restrictions are a demand-side response to a supply-side problem. Reducing evaporation from canals and reservoirs through solar coverage is a supply-side response to the same problem. They are not alternatives to each other. They are complements, working on the same shortage from different directions. The city needs both working together. The honest challenge in Colorado is more complicated than in most states, and it comes down to water law. Colorado operates under the prior appropriation doctrine, the legal framework that governs almost all water rights in the American West. Under prior appropriation, water rights are allocated in order of seniority, first in time, first in right, and a water right holder is entitled to divert a specific quantity of water from a specific source at a specific location. This system was designed for a world of simple diversions and canal deliveries, not for a world where evaporation reduction from solar canals creates a complex question. Whose water is it that was saved? If a canal company installs solar panels and reduces evaporation by 500 acre-feet per year, does that saved water belong to the canal company? To the senior water rights holders who hold the underlying rights to the water in the canal? To the state? The Colorado water legal community has been wrestling with this question, and it does not yet have a clean answer. Getting to deployment at scale requires resolving who benefits financially from the water savings, which requires legislative or regulatory clarity that has not yet been provided. The cost premium over conventional solar is also real. Installing panels over a canal costs more per watt than installing them on flat ground nearby. The additional structural engineering, the water proximate installation requirements, and the maintenance access design all add cost. For a state with abundant open land and strong solar irradiance, the pure electricity economics of canal solar are less compelling than in a land-constrained state like Japan or South Korea. The water savings case has to carry the financial justification, and quantifying the value of saved water in a prior appropriation state is not straightforward. Denver's water has always come from the mountains. The city grew up at the base of the Rockies specifically because of the snowmelt-fed rivers that flow east from the Continental Divide. For most of Denver's history, the mountains delivered. This year, they delivered the worst snowpack in 4 decades of comprehensive modern records at the worst possible time into a city that is growing faster than its water system was designed for. The canals and reservoirs that move and store that mountain water are losing hundreds of thousands of acre-feet per year to a sun that is getting stronger and a climate that is getting drier. Covering those surfaces with solar panels does not fix the snowpack, but it recovers water that is already in the system from surfaces the state already owns using technology that is already deployed in California and Arizona. The mountains will have bad years again. What Denver builds between now and then will determine whether those years become crises or manageable shortfalls. Where are you watching from? Let me know in the comments. I'm Benjamin. Thank you for listening to Watts Around the World.